We have been talking about spread rip theory and integrating from the east to west and the integrated meridional transport. We also convinced ourselves that the Taylor columns are working in the ocean because when there is Ekman pumping or Ekman suction, Taylor-Proudman theorem can be satisfied by the water columns moving south or north to stretch or compress and satisfy the condition of the fluid not being rigid parallel to the axis of rotation. But how do we deal with the ocean topography then? We can see that there are these mid-ocean ridges all over the place, plate boundaries here, volcanic islands, and so on and so forth. So how can Taylor columns work? If in fact we have shown the flow right across these mid-ocean ridges when we showed the subtropical subpolar gyres and so on. If Taylor-Proudman was true, then remembering the water tank experiment, you would expect a stagnant water column above these topographic features, but that's not what we saw when we looked at the gyres and so on. So what's happening? Well, the change in density in the vertical comes to our rescue here. Ocean is stratified. As we know, there is the surface mix layer, there is the thermocline, and then there is the deep ocean. So we saw this where the doming of the thermocline with the upwelling, the subtropical gyres, the convergence and pushing down is happening. This is top 1 kilometer, this is from the surface to the bottom. So can we use somehow these layers in the ocean to say maybe the layers can act as Taylor columns by being insulated from the bottom topography? Well, that's approximately what actually happens. Okay, so here we have, let's say, considering ocean as a simple two-layer structure with the deep ocean and let's say the thermocline layer. Remember this structure here. So there is a deep ocean that is sitting here, and then let's say this we are estimating somehow as one layer with an average density of rho 2, which is lighter than rho 1. So delta rho in this case is rho 1 minus rho 2 because rho 1 is heavier. And Taylor-Proudman theorem would just tell us that the height of the Taylor column cannot change. It has to remain rigid as it goes around on the sphere. So that just means that 2 omega over d has to be constant. What is d? This is our old height of the Taylor column we saw before, right? This is our d. So the depth of the ocean is measured with the local vertical. Ekman pumping is in the local vertical direction, but when the water moves, we looked at the Taylor columns because they have to be parallel to the axis of rotation, right? The rigidity or the stiffness delivered or imparted by the rotation is in the direction parallel to the rotational direction. Okay, so remembering again, delta rho is rho 1 minus rho 2, our old relation from the previous podcast. The height of the Taylor column is h, the depth of the water column in this case, depth of the layer with density rho 2 on top of the ocean that's hiding the topography. Let's say it's the layer below the mid-ocean ridge in the Atlantic. Okay, that's h divided by sine phi at any latitude phi. 2 omega over d is constant because omega is constant and d has to remain constant for Taylor-Proudman theorem to be valid. The book doesn't explicitly say what this is, but actually it turns out to be an important quantity called potential vorticity. Okay, you have some sense of now what is vorticity. It's a tendency of the water parcel to rotate, and F over H basically means when you have a stratified ocean and you change latitude, you're changing F, so the planetary vorticity is changing. Remember, planetary vorticity is 0 at the equator, and maximum, maybe it's the other way. It's maximum at the poles, and because on the equator you are just moving linearly, as soon as you step off, it's like you're on the merry-go-round and you step off and you feel dizzy. I don't know, some analogy, okay? So 2 omega or d comes from there. So the TP column will maintain its length, and we carry 2 omega here because the F changes. So when we look at the water column, even though omega is constant, 1 rotation per 24 hours, because we are on the sphere, local F changes. So when the water moves, it's actually moving through different F, hence its Taylor column stretching happens, which means F over H is constant. Okay, that's kind of a heuristic argument, but one can go through the math of it. So F over H is constant, where F is 2 omega sine phi. So at any latitude we can take a Taylor column, and it has to maintain its potential vorticity, because think of a ice skater. Okay, an ice skater gives herself a spin, and then she can change the speed with which she rotates. By stretching her arms, she can slow down. By pulling the arms together, she can speed up. Right? That's kind of that's kind of what's happening here. F is the planetary vorticity, and the rotational tendency of the parcel can change by changing H or by changing F. And for Taylor-Proudman theorem to work, F over H has to be constant. Okay? I hope that is clear. You can listen to it again and see what I mean. Okay? So F is 2 omega over sine phi. So what is H in this case? In the real world, H is of course the thickness of the isopycnal layers, or the so-called sigma layers we had drawn before. And F over H can be written for a continuously stratified fluid as F over rho ref d sigma dz, with a minus sign because of the density increasing with negative z. Remember, z is going down, it's negative direction. Okay, so that's fairly simple. So F over H takes the form of F over rho minus F over rho ref times d sigma dz. I think it explains why the H can be written this way, but you can look at that in the book. So here is F over H of a sigma of 26.5. So that's somewhere in the thermocline, which changes a lot with latitude. So here H is varying and F is varying. So at shallower latitudes, the isopycnal thicknesses vary a lot. Why? Because remember, you have the turbulent mix layer at the top, you have the thermocline, and then you have a deep ocean which hardly varies, right? Isopycnal thicknesses do not change much because the entire fluid column is almost uniform, so d sigma dz is very, very weak. So corresponding to that, you see that the F over H contours return on themselves to maintain F over H equal constant. Make sure you get a sense of this. So this is showing depths of these surfaces in should be in meters. Okay, so sigma is the potential density on shallow density surface in the Pacific. This is obviously the Pacific Ocean. Depth of this surface is plotted in 9.8, and the deeper surface 27.5 is shown here. Okay, so sorry, this is showing F over H, not the thickness. Okay, so you can see that F over H are being approximately maintained here when you follow these contours. Okay, if you go to the deeper oceans, they become almost zonal. Why? Because, as I said, the isopycnal thickness just runs from east to west, being almost constant because the deep ocean is hardly stratified. It's just constant density almost all the way, which means to keep F over H constant, you have to maintain F to be constant. So you just run along latitude lines. Okay, so that should give you some intuition about how, if H changes, F has to change to be, for F or H to be constant. But if you go to a place where H is forced to be constant because of lack of stratification in a homogeneous fluid, then F cannot be changed. So water parcels are stuck in this zonal band. But as we said before, the deep ocean is hardly moving, so it's not a big deal that the water is just aligned along zonal bands of F over H. Okay? It's many words, but the concept is very simple. It's just that we haven't rigorously gone through the vorticity arguments, but this relates a lot to how the vorticity in the interior of the ocean changes, knowing that vorticity is generally created by the winds at the surface. How do you impart vorticity to the layers that are below, that are shielded from the direct generation of vorticity at the surface? So the physics gets a little bit complicated, hard to do it all without the math of it, but for here, these heuristic arguments, simple arguments should suffice. Okay?